Okay, yeah. So today I'm going to talk about the simulation of magnetism. So I will try to keep the same type of presentation as the one for the displacive phase foundations. So having the main take-home messages and see what we can do, and to have it accessible for both eventually experimentalists and people doing theory and simulation. And so let's see what we can do now with that. So here I will finally here I like to present a bit the quick history of a minimal background of magnetism. And I will not present it today because I have no time, but basically this is a lecture you should have seen during the master and some. That's where I will remind you what you should know before tackling, let's say, going to understanding of magnetism at the microscopic level. Then I will distinguish how to simulate that from DFT, and we'll see that we have collinear and non-collinear magnetism. And then we see what we can do. So we'll show some examples and so on of collinear and non-collinear calculation to what it looks like, what kind of properties we can extract from it. And I will show also we can do a constraint magnetic moment that is quite useful. You can constrain the direction of the magnetic moment to explore the energy landscape for the spin and spin directions. And then we can also apply, a finite magnetic field, and then we'll see its application into the magnetoelectric response. And then I will show one of the main targets of often what we want to do is to fit a Heisenberg model against the DFT calculation to extract all the magnetic interaction parameters. And I will show you the two main methods that can be used. And I will show quickly two applications in bismuth ferrite and in gadolinium ferrite that are magnetoelectric. Okay. So I will say for the magnetism, I will say the theory of magnetism started, I will say, it was possible to make it out of the experiments of Hans Christian Ørsted. Finally, it was the first experimental evidence of that you have a link between an electric current into wire and the magnetic field, because it was observing that when he was putting an electric current into wire, the magnetic compass were deviated by this electric current. So that was the first highlight that, okay, there is a link between electric currents and magnetic field. Say. And then very soon after, because the year after, it was the famous law of Biot and Sarats, who finally made the first mathematical expression that was making the link between the magnetic field generated by a wire with intensity and so on, and the electric currents flowing to the wire, whatever the distance and so on. And so I see this was probably one of the main basis for starting the theory of magnetism. And then I'm jumping many things and so on. But then one of the first microscopic theory was coming from Pierre Weiss. And the idea was thinking, okay, if the magnetic field is coming from an electric current, so on that distance, they were thinking, okay, we have some magnets, permanent magnets, like the magnetites, and they exhibit a magnetic field, but there is no current into it. So on that time, they were thinking, okay, there are the electrons that are spinning around the atoms that are giving rise to like a current loop that is giving rise to magnetic field, and then it's forming like a kind of a dipole, and these dipoles are interacting between each other into the molecular crystals. And the idea of Pierre Weiss is that indeed this is the theory of molecular fields, and it's actually a very good feeling in the sense that it's very close to the Heisenberg model actually. And it was so good that they were able to explain the ferromagnetism and so on. And this type of theory was quite extended a lot by Louis Nel, that was the PhD student of Pierre Weiss. And Louis Nel, as we know, he extended that theory to mention that we can have antiferro magnets as a possibility. It means the global magnetization is zero, but locally you still have non-zero magnetic moments around the atoms. And then he extended that to ferromagnetism and so on and so on. I will not show all the lists of the developments he made for magnetism because he got the Nobel Prize for all these developments at the end. But up to there, you see in the 30s and so on, there were all these simple, let's say, models that were able to explain qualitatively what is happening, but quantitatively it was completely wrong. Because on that time, it was clear if it's just the electrons spinning around the atoms, so the only magnetic interaction you can imagine is the dipole-dipole interaction between each dipole around each atom. And the problem that if you take the dipole-dipole interaction and you compute what is the strength of interaction between atoms, knowing the distance between the atoms and so on, and and the thing that you can explain that the magnetism should survive up to 10 to minus 3 Kelvin. So 0.001 Kelvin, beyond 0.001 Kelvin, the magnetism is destroyed by the thermal fluctuation or even the quantum fluctuation at this temperature. And then they were questioning, okay, what is the main source of the magnetic interaction if, like in magnetite, you have a critical temperature of 1000, and then from this simple dipole-dipole interaction, you are losing like a 6th order of magnitudes on the amplitude of the magnetic interaction between the atoms. And that's, as you certainly know, that's the only solution to explain magnetism, actually, is coming from quantum mechanics. And because without quantum mechanics, you cannot explain magnetism, because actually it happens that it is not a magnetic dipole-dipole, it's not a magnetic interaction, actually, that maintains the spins aligned together inside a crystal or molecule. It is actually the Coulomb interaction, but when you treat it quantum mechanically with the spins of the electrons and the Pauli exclusion principle, then from that, then you can explain it is what is driving the magnetic interaction. It is this notion of exchange and super exchange and so on. And this is a purely quantum mechanic property that you can have. So the mean that it was for a long time, magnetism up to the beginning of the 30s. And I will say the first experimental measurements of antiferromagnet and so on were coming from in the 40s, 50s. And so as you can see, the magnetism explanation of magnetism is coming actually quite late with respect to some other fields, like the displacive phase translation, for example, and so on. And so out of that, finally, the minimal knowledge, if you want to make a microscopic simulation of magnetism and to understand what's happening into the crystals and molecules, at the end, you need to understand this quantum mechanic interaction. That's probably something that you have seen is the origin of electrons. So why within an atom, if you have all the electrons, you start to populate the electrons into the, let's say, the d orbitals, and these electrons prefer to align ferromagnetically between each other. This means the intra-atomic exchange is a Coulomb-Coulomb interaction that can be reduced to a spin-spin effective model, that is the Heisenberg model. We're going to see it after. And this spin interaction is driven by the Coulomb interaction. And within a single atom, you have all the wave function are orthogonal. There is no overlap. And this is what is favoring the ferromagnetic interaction between the electrons. This means that already on that time, okay, we're able to explain, okay, on a single isolated atom, the electron-electron interaction will favor a ferromagnetic ordering inside an atom. And now it was not, actually, it was still a mystery in the sense that, okay, between the atoms, we knew after Louis-Néel and some different measurements and so on that we have much more antiferromagnet than ferromagnets. And actually, when trying to do exactly the same quantum mechanical calculation to know the interaction between electrons, but between the atoms, it's like if you take the hydrogen molecule, so we approach two hydrogen atoms, and you figure that if you solve that quantum mechanically, you figure that the ground state, the magnetic ground state of this atom interaction is actually antiferromagnetic. So you do the same calculation, and it means that the direct interaction is antiferromagnetic between the atoms. So within the atom is ferromagnetic, between the atoms is antiferromagnetic. And even if you put a ligand in between, like the oxygen, fluorine, or nitrogen, and so on, you use what we call the superexchange, is the magnetic interaction between, let's say, ion, oxygen, and ion. This magnetic interaction is also favoring antiferromagnetism, mostly. So that's why, from the quantum mechanics, then we are able to explain, okay, why you have much more antiferromagnet than ferromagnetic systems. And then on top of that, everything is coming from actually the energy levels of the, let's say, the d orbital for the transition metals around the atoms, because this is what is going to give you how much magnetic moment you have on each atom. And this means that you need to know how the energy levels are splitted by the cations that are around. And this is the theory of Chrysafield theory, Chrysafield splitting theory. So how the energy of each atom are split due to the presence of the other atoms inside the crystal of the molecules. Then you also have the molecular orbital theory, in the sense that when you have a binding between two atoms, you have a bond, and you form a bonding and anti-bonding. It means you have mixing of the wave functions. And these bonding and anti-bondings can also drive different strengths between the magnetic interactions. And of course, on the top of that, you need to include the spin-orbit coupling, because without spin-orbit coupling, any spins can orient along any direction in the 3D space without any cost of energy. So the only term that allows to maintain the spins to be aligned along x, y, z is the spin orbit coupling that couple the s spin of the electrons and the orbital moments L of the atoms. As we can imagine that when we approach two atoms, you have a bonding. So you have some direction of some orbitals are oriented in some bonding direction, and this is going to fix the spin orientation inside the system. And of course, all of that inside the crystal, you can use symmetries also that helps you to describe the magnetism that you have in your system. Okay, that's I would say the minimal background. This is basically the outline of my lecture for the master students. So I will consider that you're supposed to have this minimal background as a master students now starting a PhD. So let's suppose that you know that, and the idea is that I was mentioning that all this magnetic interaction can be reduced to an effective spin-spin interaction. Even if the interaction is coming from the Coulomb interaction, we can reduce it to like a dipole moment interaction. But you see the expression here from the general Heisenberg model you can build. That's the thing that's the largest interaction in this SS interaction, SS prime. And this coupling constant that drives the magnetic interaction between the two is what we call the exchange, the direct exchange or super exchange. And this is the strongest magnetic interaction inside the crystals and molecules. So the main, we say the critical temperature is going to be driven by this super exchange interaction. Then when you add the spin orbit coupling, you also have orientation favoring and so on. And you also have a second term into the interaction that is, you see here the first main interaction is a dot product between two successive magnetic moments. And you have a second term that is also giving you an interaction that is a cross product between two spins. And what does it mean? That means that here this S dot S prime interaction favor parallel orientation of the spins, while this one, to minimize the energy, will favor 90 degrees orientation of the spins. But the thing is that this is the coupling constant that is in between this S cross S prime interaction is what we call the Jarzki-Moria interaction. And the thing is, because the Jarzki-Moria interaction is coming from the spin orbit coupling, it is often much smaller than the super exchange interaction that is driven directly by the Coulomb interaction. So often this Coulomb interaction is of the order of a few milli-electron volts, while the Jarzki-Moria interaction is of the order of a few 10 or 100 micro electron volts in most of the cases. And then at last you have a last term here that is, noted here S phi S is simply, you see, it's between two magnetic moments on the same sides, and it's simply going to give you what is the main spin orientation around the atom inside the crystal. So on each atom you have the spin, the magnetic moment we prefer to be aligned along X, Y, Z, or whatever combination of these directions. And this is going to be driven by this kind of interaction that is the so-called single ion anisotropy. So what is the anisotropy? Means what is the cost of energy if you flip the spins from X, Y, and Z direction in the 3D space. And so the idea, since this is, let's say, the main, we can extend also this model with a more complex thing, but let's stay with this, this minimal Heisenberg model, I would say, right now. And the idea here, that's basically, okay, with that kind of type of interaction, you can explain many things regarding the magnetism. And the idea is that now, okay, you want to simulate spin dynamics or do a second principle calculation and so on. And then you want to estimate what are the strengths, what is the strength of the different magnetic interaction, means the super exchange J, the Jarzki-Moria D, and the single ion anisotropy. And one of the best tools to do that would be to use the first principle calculation, because you treat everything quantum mechanically. And as I mentioned on Tuesday lecture, one of the best method for that is the density functional theory, the DFT. And so I will not go spend so much time, I already presented that on Tuesday, but so the DFT allows to reduce the many body problem into a simple picture using the density that is a scalar value of the electrons, so quantity of electrons, let's say, in the X, Y, Z, for each X, Y, Z position in the space. And the thing is that, I mentioned that before, so the DFT has been built right up with electronic density, but now we want to generalize that for magnetism. And then there are two possibilities. The first possibility is to do what we call a collinear magnetism. And in the collinear magnetism, okay, we can, the tip to implement that into the DFT is to suppose, okay, now we have a density, the electronic density rho that is here, can be decomposed into the density of the electrons we spin up, rho up, plus the density of the electron we spin down. That makes sense. And this means that the energy coming from the DFT can be expressed, instead of simply the electronic density, can be expressed into two electronic density, that's for spin up and spin down. And now if you plug that into the connection Hamiltonian that I'm showing you it here today, basically you have the kinetic energy plus the potential energy due to the charge of the atoms, plus then you have the Hartree interaction between the electrons, VH that is here. And the construction of how the DFT is made, that's everything that is left aside this interaction is put in what we call the exchange correlation potential, or what I call VXE here. And this VXE potential is actually, if you look into all the terms here, is the only one that depends on the spin channel, that I call it the sigma here. So I mention that because you see that magnetism is already a small quantity interaction with respect to all these other interactions that are here. The spin-spin interaction is quite small. And you can see here within the DFT expressions, the Hamiltonian that is here, basically only one term is directly acting on the magnetism, is sensitive to the magnetism, which is this exchange correlation functional. So it's good to mention that because we see that it is the main, I will say, limitation of the DFT is that this exchange correlation functional is basically unknown. And we don't have an exact expression. And so that's why we have many approximations to tune this exchange correlation functional. And the thing is that because magnetism depends only on that, it is a small energy interaction. The magnetic interaction are quite small with respect to the Coulomb interaction. And then you have only one, the main potential within DFT that depends, that is going to act on the magnetism, that is going to drive the magnetic interactions and ground state and so on. This exchange correlation functional is unknown. So I will not spend so much time on that because Julien Varillon will discuss with much more details about these different approximations. But just remember that for magnetism, this exchange correlation functional is actually quite important, and is why any parameter going to tune inside this exchange correlation functional will strongly affect the magnetism. So it's why magnetism is much more difficult to simulate than a regular insulator or the electronic density. Okay, so this means that, okay, now we have to minimize again the energy with respect to the density, but now we have a density that is up plus down, and the magnetization is coming out from it naturally, in the sense that magnetization is simply going to be the difference between up and down. So if you have more electron with spin up than spin down, then you have a remaining non-zero spin and so magnetization in your system. So the magnetism is really easy then to extract. And I will just to mention here at this level, here the magnetization is actually not a vector. Here at this level, the magnetization is a scalar, in the sense there is no vector, it's just up minus down. This is the quantity of electron up, quantity of electron down. So it's going to give you, it's a scalar, means it has a positive and negative sign, an amplitude, but it has no orientation in the space. Okay. And the thing is that if you do a DFT calculation, and mostly if you have an antiferromagnet, the total magnetization is going to be zero. So it's not going to be very convenient in the sense that you will see zero while potentially you have magnetic interaction inside your system. And the easy way it is done into DFT is that, okay, how to estimate the magnetic moment around each atom? We simply take a sphere around each atom, and then we integrate the density up and the density down and make the difference. And this means that we can have an estimation of how much is the magnetic moment around each atom by making an integration around this sphere. And this approximation is working, supposing that the magnetism is coming from electrons that are well localized inside the spheres, which is often the case for D and F electrons, where 99% of the magnetism is coming from the D and F. So this is quite good. And here I'm showing a specific, really directly the output of the Abinit code, for example, here for the ion bulk. And you can see here that the ion bulk is only one atom per unit cell. And you see you define here the radius of integration that is in Bohr here, 2 Bohr. And then you see you can integrate the up density, the down density. You can make the sum of the two, that is the total density. And then the difference between the two is giving you directly the magnetic moment of your system, of your atom, sorry. This means here we can see that for the ion, we predict from the DFT calculation here magnetic moment that is about 2.23, which is not so far from the experiments. And the thing that here we have can make the sum, and the way to check if this integration inside the sphere is correct, that's you can make the total magnetization, that is the sum of all, if you have more than one atom, you have the sum of all the magnetic moments of each atom that give you here 2.23, but you can have also the total magnetization that is exactly calculated like that, so the whole unit cell that you have by default from the DFT. And then you can check that indeed that the two are very close to each other, and this means that, okay, this approximation of interaction inside the sphere is valid for at least here the Heisenberg. But always check this, if for those doing the DFT calculation, for doing magnetism, always check that this is fulfilled. Otherwise, if you have something more itinerant, then you might be wrong by estimating a local magnetic moment on the atom. Okay. Now, as I'm saying, that this is, as I'm saying, here there is no spin direction, but we can add the spin direction. And as I mentioned before, we need to include the spin orbit coupling. And then when we add the spin orbit coupling, it's from the Dirac equations. That's the wave function is not anymore a simple wave function with one component, but the wave function has two components. It's a spinor, and then in the spinor, we have the up and down component for the two spin channels. And this means that the density is simply going to be equal to this wave function square. And this means that the density is not anymore a single value, is a 2x2 matrix. Because if you multiply the wave function by itself, then you have up and down components, and up down and down up. And then this, using the Pauli matrices, you can also develop that into the fact that this density matrix is actually equal to the electronic density that is non-magnetic, plus the magnetization along the z direction, or minus the magnetization along the z direction along the diagonal. And then you have the magnetization along x plus or minus imaginary part of the magnetization along y in the off diagonals. Okay, this means that's okay with the this non-collinear description with the spinors. We have the density. If we express it into the density, we can have access to the electronic density that is non-magnetic, and the magnetization density that is closed along x, y, and z. This means that we can have a resolution of what is the main direction of the spins in the space, in the 3D space, if we can plug that into the DFT. And this is what we do. That means that we take the DFT equation. You suppose that you have a spinor instead of a regular wave function. And now your Hamiltonian is not anymore a simple Hamiltonian. It's a 2x2 matrix again, because we have a 2x2 matrix for the density. So expressing that with the density, we have a 2x2 matrix. So we have 4 components for the Hamiltonian. And here again, we have the kinetic energy, potential energy due to the nuclei, and the Hartree interaction energy. And then we have again this exchange correlation functional. And here again, only this exchange correlation functional is dependent on the magnetization of your system. And so here again, and then when you do non-collinear magnetism, is what we're going to see when we have canting or spins or things like that. The magnetism is even much smaller than the collinear case. So this means here again, any single modification of the exchange correlation function can have a very drastic effect on the non-collinear magnetism. So you need to be careful of what you are doing. And often I say that you need to explore carefully what is I would say the phase space with respect to the parameters you use for this exchange correlation function. And here I give you again the same example for with the ion. And then of course you have to add the spin orbit coupling into the potential. That is what I'm supposing here. And here again for the ion, you see here if I start my calculation putting the spin along z, and you can see here you can integrate the total density inside the spheres again. And then you can also have access to the magnetization along x, along y, and along z. And we can see that's, okay, ion is a collinear magnet, so we don't see any components of the magnetization along x and y. Here the few digits I have, it's just the numerical numbers. And again, you can also integrate the total magnetization inside the spheres and compare with the total magnetization that is calculated exactly in the whole unit cell. And then I would like to mention here something, because we have experimentalist answers, which is quite nice. Often there is, you have to be careful. This is what I'm mentioning here at the bottom of this slide. What we call non-collinear calculation doesn't mean necessarily what experimentalists call non-collinear magnets. I'm going to show you an example just after, because often experimentally what is called a non-collinear magnet is when we have weak ferromagnetism. And when you have counting of the spin, so weak ferromagnetism or weak antiferromagnetism. While in the DFT, when we call a non-collinear magnetic calculation is because we have the spin orbit coupling, we can have a resolution X, Y, Z. But as you can see here, the Heisenberg is a collinear magnet experimentally, but here we did a non-collinear calculation. So just to mention that, be careful when we say non-collinear calculation doesn't mean it is a non-collinear magnet at the end. Just to be sure it is clear for everybody, because I met often this kind of I would say discussion, misunderstanding regarding this non-collinear calculation and non-collinear magnets at the end. Okay, so here just to mention again that this is something I was mentioning that the often we have this approximation for DFT plus U for this exchange correlation function, but I will not go into detail because Julien Varignon will present all the details with that and all the problems you can face. And then we said that this non-collinear magnetism is really extremely sensitive then to this exchange correlation function. I give you some references here to see that in some cases, without an experimental measurements, I'm not sure we can really predict in advance with DFT what is the exact really ground state non-collinear magnetism. Mostly for non-collinear magnetism, I would say. And another thing as well, that's often we say, oh, spin orbit coupling is a small interaction, we have small countings and so on, and often you need to increase a lot of the numerical precision. And actually the numerical precision is not coming from the discretization of the K point for the reciprocal space or the cutoff energy for those who know that the plane wave expansion that we do, that's supposed to be infinite, so we have to cut at some point. And actually, this is not too much demanding with respect to that, but it's really demanding that the precision of the self-consistent calculation, when you minimize the energy or the density, this has to be really fine-tuned. This is the main important part. So it's a self-consistent calculation precision that is important more sometimes than the numerical cutoffs that you put for discretization. Even if this is important, you have to do it anyway. That's clear. Okay. And then here, something that for those who have the slide, you can have access to that. So that you have a multiple orbital occupation and spin minima and so on. The energy landscape with magnetism start to be quite complicated, but this also will be partly discussed by Julien Varignon. Okay, let's go with a more complex example. Here we start with yttrium chromium oxides. And I start with that because chromium 3+ in oxides, in an insulator, is one of the easiest systems to simulate from DFT, because even with this exchange correlation function, without any very complex advanced function, you can predict correctly the non-collinear magnetism. And this yttrium chromium oxide is a perovskite, but in the ground state it is distorted. It is this the most common. This is the PNMA orthorhombic space group, while you have the oxygen octahedra are tilted and rotated between each side. And the thing is that in this PNMA space group, this is valid for all the PNMA perovskites, magnetic perovskites actually, basically for yttrium chromium oxide, it is a non-collinear antiferromagnets. So here, if you see all the rows here, so globally it is an antiferromagnet. It's a G-type antiferromagnet. So all the spins with one direction are surrounded as the first member with spins in the opposite direction. And then the thing that then we have a small deviation away from the main crystallographic orientation, let's say the Z direction. And then you have a small deviation in one direction and along the Y direction that is, with all the spins in the same direction, give rise to weak ferromagnetism. And then on the third direction, you also have a small canting, a small deviation that is actually resulting with a weak antiferromagnetic order. So if we do that from DFT, you see here is more complex. So I show you the output from Abinit code here again. So we do the same. So for every atom, we define a radius of integration around each atom, and then we see how is the magnetism. And this is the output from a collinear calculation. So without spin orbit coupling, and this means that we don't have a resolution of the X, Y, Z direction. But as I was mentioning, here we have the up density, the down density. Then the total one is simply the sum between the two, and the difference will give you what is the amplitude of the magnetic moment. And we can see here the chromium, I've put the chromium on atom 5, 6, 7, and 8. And we can see here we have a magnetic moment of about 2.5 bar magneton. And we can see here that's I started with a G-type antiferromagnetic, and we indeed have, after relocation, a G-type antiferromagnetic, which is in this case you see magnetic moment that is plus, minus, minus, plus ordering in this unit cell. And again, here is why it's important to have this local projection, because you see the total magnetization is 0 because it is an antiform magnet. But then you can question, okay, but before we just mentioned, even experimentally, it is observed to be a weak magnetic system. And you can see here, without spin-orbit coupling, you cannot see that you have a weak ferromagnetism. You can just see that the global magnetization is 0, but you clearly see non-zero magnetic moment on each atom, but it is globally non-magnetic. But that is why you need to switch on or do the calculation with non-collinear, add the spin-orbit coupling into your calculation, and you will do the same. And then now you see the output of the relaxation. So we have the total density, magnetization. Now we have magnetization along X, along Y, and along Z. We can see that it is more or less 0 on all the atoms but the chromiums. And we can see that I started the calculation with spins along Z. And we can see that indeed, globally, the system stays, you see, you have a magnetic moment of about 2.43. So most of the magnetic moment is on the chromium along the Z direction. It is also still a G-type. But we can see here we have something that is slightly non-zero away from the Z direction. And if you check carefully, you see indeed along the Y direction, we have about 0.06, 0.06, 0.06. So we have all the magnetic moments have a small components along Y in the same direction. This means that along Y here you have, if you make the sum here, you have a non-zero magnetization. And if you do the look along the X direction, you also have a small deviation, is non-zero. But you see here you have minus, minus value and plus, plus. This means that the small deviation along the X direction is this time making a sum that is 0. This is why what you observe here, what is observed experimentally, is that okay, globally it is a G-type antiform magnet, which spins along Z. But then you have a weak ferromantic moment along the Y direction. This is the weak ferromagnetism. And then you have it is a weak antiferromagnet magnet along the X direction. And then you can compare with experiments indeed what is observed. And this can be also analyzed, checked by symmetry. And by symmetry, you can prove that if you have the G-type of G-type magnetism along Z, then you should have a weak ferromagnetism along Y and a weak antiferromagnetic along X. So it's why here I will not introduce the symmetries, but when you do a non-collinear calculation, as you can see, the values here you see of the magnetic moment is really, really small. You see the total magnetization is about 11. The magnetization on the main direction is about between 2 and 3. But the cancelling is, you see, is 2 orders of magnitude smaller. 1 to 2 orders of magnitude smaller. So this is a really tiny, tiny, small interaction, but as you can see, DFT can have the resolution of it and get it. Right. And now if you continue, that's, as I mentioned, that's, yeah, but you can also estimate, okay, I put the spins along Z because experimentally it is along Z, but I can also suppose that to put the spins along Y or the Z or the X direction. But from the DFT, you see we minimize the density to get, or minimize the energy to find the ground state energy. And this means that for each spin direction, I can estimate what is the energy. This means I can have access to the magnetocrystalline anisotropy as well. And this is just here the output of Abinit again here, but you see here putting, which just showing for the chromium, initializing the magnetization along the X direction with the G-type, or here on bottom along the Y direction. And we can see, okay, after the relaxation, we find, okay, globally here it stays G-type antiferromagnets, but then we have a weak antiferromagnetic canting along the Y direction, and we also have another type of antiferromagnetic canting along the Z direction. So it means that when we have the spins along X of the G-type, we have a canting that is allowed along Y and Z, but both of them are antiferromagnets. And it is indeed confirmed by symmetry analysis. And actually, now if you put the magnetization along Y, so it stays mostly G-type along Y direction, but then you have a weak antiferromagnetic canting along X. You see the sum is 0. And then you have a weak ferromagnetic canting, like it is when you put the spin along Z. Now along the Z direction, that is non-zero. And it again is what is predicted by symmetry, simple symmetry analysis. And this means that, okay, we can have now, we have a 3 calculation with spins along X, Y, Z. We can compare the energy. We can see which one is has the lowest energy. And this is what I'm mentioning here in the small table here. By putting the spin direction along Z, Y, or X, then I can compare the energy. I suppose the spins along Z to be the 0. And I can see here that the energy for putting the spins along Y or along X is higher by a few hundred of micro electron volt. So you see the energy difference is really small, but we can have a resolution of it. And indeed, experimentally is what is observed. We have a small anisotropy of the order of a few hundred micro eV. And experimentally, it is predicted as well that the spins are along Z. So be careful, because here I was mentioning the chromium is just for for illustrating the result that chromium without any special tricks of the exchange correlation is working quite fine, because we reproduce the experiments. But be careful, in 90% of the cases, it's not as easy as that. But you have some cases where it can be done quite easily. Okay, now another thing you can do as well, we jump to another example, that's instead of having the spins around X, Y, Z, you might want to know what is the really energy barrier between the two. And here I show you an example going back to the ion BCC bulk, because it is easier. And it's something we can do. We can constrain the magnetic moments in some specific direction and compute the energy from DFT. And this is what I plot here for the ion bulk. You see the red dots are the calculated energies from DFT for different spin direction going from Z to X, and I put a small rotation going from X to Z. This is the example here of the input. You see my initial magnetization is along Z, and step by step I project some magnetization, transfer some magnetization from Z to X, and it's giving where it can be transferred to a given angle. And then I can compute the energy for all this spin orientation, and then I have the energy landscape that is shown here. And as you can see, for the ion bulk here, you see it's even much smaller. It's of the order of 0.4 micro eV, but you can see that the DFT can have this kind of resolution is possible from DFT. There is no problem. And it's consistent also with experiment. That's okay. The anisotropy in ion bulk BCC is extremely small because it is cubic as well, and then it is indeed of a few is less than 1 micro eV of amplitude. Okay, this is something we can do as well. So explore the energy landscape for the anisotropy. And another thing we can do as well is to apply a magnetic field, because in the connection potential we can simply add the Zeeman potential, that is simply mu b times mu 0 times the value of the magnetic field. And as I was showing you, we have a 2x2 component of the magnetization density in DFT, so we have a 2x2 potential, and then we just have this Zeeman potential to add into the DFT. So it's very simple. And out of that, then this means that you can apply a magnetic field and plot what is the induced magnetization, extract the magnetic susceptibility. And this is something I'm going to discuss more now, because we're interested by that mostly, and I am interested by that. You can also, when you apply magnetic field, you can plot the magnetization, but you can also plot the polarization. And then the line that is drawn from induced polarization due to magnetic field is what we call the magnetoelectric response. And I'm going to discuss a bit more later to show you an example for this magnetoelectric response. The magnetoelectric response is what? Is basically that is a crystal where you can tune the magnetization with an electric field or tune the polarization with a magnetic field. So it's a cross response. And it's really important, really interesting crystal response, because you can have many applications for mostly spintronics and computer memories, because you see if you can write magnetic memory using an electric potential, it's going to cost much less energy than if you have to write it magnetically, directly with electric currents. And then it has one of the main applications is going to be out also that can use to be as sensors to replace the squids, that we have better precision and also working at room temperature eventually, if the crystal is working at room temperature, and so on and so on. And so for this magnetoelectric response, so basically is that if you have a crystal that is non-ferroelectric, that is non-polar, this means that you can induce the polarization through this alpha tensor with an applied magnetic field. And the other way around, you can apply an electric field and compute what is the induced magnetization, give rise to the same alpha coefficient that is a linear magnetoelectric tensor in this case. And of course, it can be nonlinear. And this is quite a material challenge in the sense that it needs broken space and time inversion symmetries together under the applied field. And then it is often satisfied at a relatively low temperature, and the response is extremely small. In SI units, the response is often of the order of a picosecond per meter. And here I try to draw a log line of different compounds that has been reported up to now. This is not exhaustive, and you can see that you have many that have the order of 10 to 100 picosecond per meter, which is quite small. And we have some new systems here with much larger response that are coming out from the past 10 years, I would say. And the deal, okay, now you want to simulate that from DFT, but I've seen that this means if you want to do that, to have the Zeeman potential, you see, is a non-collinear magnetism, because you need to know when you apply magnetic field in a given direction, you want the spins to be tuned with respect to this field or with respect to this direction. And this is what you can do from DFT, and from DFT we can apply a magnetic field, but we can also apply an electric field in non-collinear magnetism. And this means we can check, or we can compute, we can estimate that if indeed applying a magnetic field and using a polarization give rise to the same magnetic response that if you apply an electric field and you induce a magnetization. And these are the two calculations I done here with Abinit for chromium 203. And again, this I told you the chromium 3 plus in insulator is quite easy to simulate. So, and it's what you observe here. You see, this is the induced polarization under an applied magnetic field. As you can see, the polarization is really, really small, but you can get the resolution of it. And then for a different amplitude of magnetic field, you draw the line, and the red curve is the total one. And you can see that if you extract the slope from that, you find a magnetoelectric response that is of the order of 1.5 picosecond per meter. And it's an extremely good agreement with the experiment that is that predicts that is supposed to be a 0K of the order of 1.6 picosecond per meter. So it's pretty good for such a very, very small response in the crystal. And then here, I wanted also to check, okay, now if I apply an electric field and I plot the magnetization induced by this, by different amplitude of electric field, and again, we can extract the slope of this line, and I find that is something that is of the order of 1.48 picosecond per meter. That is exactly the same as the one calculated with applied magnetic field. So that means we can be confident that the implementation in code is correct. And that's also this increment 2-3 at least, that we have indeed a strictly equivalence between applied electric field and applied magnetic field with respect to this alpha tangent. They should. Okay, and now the next step, as I was mentioning, that at the beginning we had this Heisenberg model. And in many cases, what you want to do is to estimate what are the superexchange, Jauss-Moria, and single ion entropy strengths into your system, and eventually do a second principle calculation or spin dynamics in this case. And there are two ways, I would say 2 ways since a few years at least, and we see, but the first way to do it is to do what we call a total energy calculation or direct methods. So it means that you want to compute J, D, and this phi interaction. And the idea, for example, if we hit to extract the J's, and you say, okay, what you do, okay, as I mentioned you, that you can do a DFT calculation for different magnetic ordering. And you do that with ferromagnetic, you can do for ferromagnetic ordering, for the A-type antiferromagnetic ordering, the C-type, the G-type, the E-type, and so on. And for each of them, you have an energy. But for within this, the energy difference between each of them is only the magnetic interaction. If you freeze all the atomic position and so on, you can suppose that the only thing that has changed the energy between each magnetic order is the magnetic interaction. And this means that, okay, this means that the energy difference between E1 and E2 will be only simply driven, if we don't look at the direction right now, it's going to be simply driven by J. And this means that, okay, if you have, I know, 6 different J to compute to have your complete Heisenberg model, this means that you need at least 6 configurations like that to have the energy, and then you can solve numerically this kind of set of equations. Because you see, for each type, you have a given energy that is going to be given by the, let's say, suppose here only the superexchange energy. And means for each type, you have a different energy coming from the superexchange, and then you can solve that for at the end for the number of interactions you want. For the Jauss-Moria, you can do the same, but now you have to add different spin directions along X, Y, and Z. But basically, it's the same. You do different configuration, you fit. And then you solve a set of equations with different parameters against the DFT energy, basically. This is quite convenient, quite easy method that has been used for a very long time, since the beginning. And the only problem that you need, if you have 10 super exchange parameters, you need 10 magnetic configurations to be calculated. And then if you want to go, if your magnetic interaction is beyond the unit cell, you need to make supercells. And it means the calculations start to be heavier and heavier. You have many calculations to do with heavy supercells to do. And the problem that in some cases, you can end up in some troublesome cases where some of the magnetic type are not converging. But sometimes some DFT calculations are easy to do. And in some cases, some magnetic ordering can be very cumbersome to converge. And so you don't reach the convergence, and then you are in trouble because if you need 10 J's and you have only 9 configurations that are working, you are in trouble. You are stuck. And another problem is that often, like it is the case for the ferromagnetic solution, the ferromagnetic solution can be metallic, while some of the other antiferromagnetic solution will be insulators. And in this case, it is a problem because it means that the energy difference between the ferromagnetic, the metallic one and the non-metallic one is not only due to the magnetic interaction. This means that you cannot use it to fit your model. This means that you need to find more other solutions, other magnetic ordering that are consistent between each of them. So it is simple at the beginning, but it can be you can end up into a trouble at some points, depending on the system you study. We say in many cases it is working quite fine. And now we have developed, I make a bit of advertisement, but I think it's going to be quite useful. I'm calling for users for testing. And the idea now is to say, okay, it's something that has been developed by Cocorain in 2015, is to say, okay, we can use also another method that is used for metals, in metallic community mostly, that we can use the green functions. So instead of expressing keeping the wave function, you use the green functions. And the idea here of this paper is, okay, for plane wave codes, we can compute the Vanni function that are quite well localized. This is something that is quite standard now with the Vanni 90 tool. And from the Vanni function, you can build the green functions. And the interesting thing is that from the green function, you can extract all the J parameter, for example, here. When I say all of them, this means that you can extract at any order, at any distance, and any order, basically, the magnetic interaction. And this, you can do it with a single point DFT energy. You just need one wave function for one magnetic ground state, for example. And out of that, you can extract all the magnetic interactions at all the distances. I'm not going to discuss the theory, just to show you the equation here, but we have no time here to go into the details. But here we have published here a paper mentioning this method, and we also have developed a Python script that is going to help you to extract all the magnetic interaction. And it is interfaced with Vanni 90 to compute the Vanni function that is interfaced with plenty of plane wave codes. And also it is interfaced with some other code that don't need Vanni 90 because they are already localized wave functions like CSTAR, OpenMX, or GPAR. And then out of that, the code also is outputting the input for spin dynamics codes like Vampire or multi-unit and so on. And the thing I show you the example here, this is for bismuth ferrites. And this means that you can take only one DFT calculation, and then you can extract all the magnetic interaction. Here I show you only one J interaction between the two ions here, okay, for bismuth ferrites. And here you list for, and then you can have a list for if you can add 1, 2, 3. You can go at any distance as you want. You can do up to 1,000 ions if you know that's the rate of from decay. And then for each ion-ion pair of ion-ion, you can have the super-exchange calculation that is outputted. And the thing is that you can also extract the biquadratic term. You can also calculate the Jolsky-Moria. But if you need to add the spin-orbit coupling, of course, into your calculation, and with Vanni 90 as well. And you can also calculate the anisotropic super-exchange interaction. And the thing, and basically, all of that can be calculated by simply using mostly 1 or 3 in the case of non-collinear DFT calculation, instead of doing plenty of total energy for different magnetic phases, as it is done in the direct method. The interesting thing as well is that you can do a band-by-band decomposition of the super-exchange. This means that when you have a magnetic interaction between two cations, you can explain, okay, it is large, and it is large because of this band and this band in intercrystal. So this is really a new tool that we have output this year, and now now we are collecting the different users user testing, and so actually right now we are converging to something that is quite stable. And as I mentioned, because you can compute the superexchange at any distance, this means that you can do a Fourier transform and directly calculate the spin dispersion of your system. And this is here the case for, thanks to Sebastian Meyer, who gave me the plot for bismuth ferrites. But you can see you can plot the spin dispersion for any system, but starting from only a single point energy calculation. Another interesting thing as well is that, as you can see here, it means that you can see, okay, where is the lowest energy ordering for the spins, and you find that it is, with respect to the cubic phase, it is the R point that is correspond to the G-type antiferromagnetic, which is the case in bismuth ferrite. But the thing is that the other interesting thing is that even if you do the calculation that is not in the ground state magnetic phase, doing the spin dispersion, you can recover what is the ground state magnetic phase anyway, which is quite convenient. This means that even if you are not in the magnetic ground state, you can still compute the superexchange parameter, the magnetic interaction that are still valid even for the ground state at the end. Or that can help you to drive, okay, you are not in the ground state, what is the ground state? You do that and you say, okay, if you did the calculation at the X points, for example, here or at gamma, then you can say, okay, your ground state is actually at R and not at gamma, which is quite convenient as well. And then I was saying that once you have this, all the parameters calculated, you can plug that into a spin dynamic code, and then you can extract, here just an example, see the specific heat, the magnetic susceptibility, or the magnetization versus temperature for any kind of system on which you have calculated the magnetic interactions. And let me see for the timing. Okay, some time. And then let me show you a more complex example. He just from my PhD student who is working here on the rare earth ferrites. And you see, these rare earth ferrites are magnetoelectric, are known to be magnetoelectric, and they are amongst one of the largest magnetoelectric response that has been recorded. And this rare earth ferrite and chromite actually have very, very, very rich magnetic and magnetoelectric phase diagram, because they can exhibit magnetization reversal. So it means that you have is a PNMA phase like the yttrium chromium oxides. So you have a weak ferromagnetic canting, and this weak ferromagnetic canting can either be amplified when you cool down the temperature, or it can be decreased and even reversed with respect to the initial state. And this is due to the interaction with the rare earth F electron that I'm going to show you after. And then and what is also observed is that you have a magnetization reversal of the weak magnetization direction amplitude. But you can also have a spin reorientation in the sense that if you start at high temperature with a given magnetic ordering, this is a G-type along Z with a canting, weak ferromagnetic canting along X, and then when you cool down, you have a smooth transition towards another state. So it means the spins go from one direction to another one, and then you cool down the temperature. And here again, this can be explained only if you take into account the F electrons of the rare earth as being magnetic as well into the system. And see something that means you have two magnetic cations, the rare earth one and the ion. And the thing is that the temperature where the rare earths are modifying the weak ferromagnetic canting and the easy axis of the ion is beyond the net temperature of the rare earth. And it is like that because the rare earth is paramagnetic beyond 10 Kelvin. But this means it's paramagnetic. This means it's going to feel the magnetic field that is given by the ion. So this means that the ion magnetizes the rare earth, and as a feedback, the rare earth is going to be magnetized, is going to interact with the ion. And this means that you have feedback between the two that give rise to this very complex phase diagram at the end. And this is the experimental measurement for the gadolinium ferrite, for example, from this Tokura paper in 2009. And what I show also for the gadolinium ferrite, it is also magnetoelectric. So here at zero applied magnetic field, you have a non-zero polarization. And when they start to apply a magnetic field, here we look at the blue curve. And then the polarizations start to decrease non-linearly up to zero. But the modification of the polarization here is quite large. It's much, much larger than what you can observe in column 203, for example. And then we wanted to simulate that at the end. So just to show you, it's not to describe that. You can have a look at the paper. It's just out since the last week, actually. You can build a Heisenberg model where you take into account now the spins of the ion and the spins of the rare earth. And then you have to take into account means the superexchange between ion, between rare earths, and between ion and rare earths. And the same for the geoschemeria. For the geoschemeria, you need to take into account the interaction between the ions, between the rare earths, and between the rare earths and the ions. So that you can fix that and extract all the magnetic interaction parameters. And you can plug that into a spin dynamic code, just at 0K to be as close as possible as the Tokura's paper experiments conditions. And then we wanted to, we did the computer experiment after the fitting this model. So then we added the exchange friction effect into the system, means how much the polarization is affected by the change of magnetism. And then when we do the spin dynamics and we extract how the polarization evolves with respect to applied magnetic field, and we recover exactly this nonlinear evolution of the polarization. We see almost a cut, the disappearance of the magnetization and the polarization around 4 Tesla, which is quite in good agreement with this experimental measurement that is here. He's in a kilo Herschel, which means his 40 is 4 Tesla. So we are quite glad because you see when you fit this kind of system on a complex, quite complex magnetic interaction and so on. Some are very small, some are very large and so on. But in the end, we could actually make the simulation of these rare earth ferrites at the end. And you can find, if you want more details, you can find the paper. He's still on archive. Okay, I think I'm just on time, and I'm just going to thank you for your listening.